Hello students. This brief video will lead us through the basics about Lewis dot structures for AP Chemistry. In a Lewis dot structure, we are doing our very best to satisfy the octet for the elements involved in bonding. We draw element symbols. Each element symbol represents the nuclei of that element and the inner core electrons. We will then position valence electrons as dots around the element symbol, assuming that there are 4 sides around each element. Usually the standard procedure is to begin on the top, placing the electrons by themselves and then doubling up. So for carbon, it will be 1, 2, 3, 4, and you're set. For oxygen, and it's 6, 1, 2, 3, 4, 5, 6. Now, of course, we can vary from this, but that's usually the method in which we'll start. When electrons are being shared between elements, they are drawn as a dash between the element symbols. That's where we're going to draw that sharing is occurring. So if there are electrons being shared between element A and element B, a single dash will represent that. And a single dash represents the sharing of 2 electrons, or 1 pair. That is what we would call a single bond. Perchance, there could be the sharing of 2 pairs of electrons. That would be a total of 4, and that would be a double bond. You can have up to 3 pairs between 2 elements. That would be a sharing of a total of 6 electrons, and that is a triple bond. You cannot share more than 3 pairs between 2 elements. You've just run out of space, and we'll talk about that when we get to hybridization, that kind of thing. Now, of course, an element can have a double bond on one side to a double bond to another element on another side of it, but it can't share more than 3 pairs between 2 different elements. Our structures will not have any lone remaining electrons, and we are building small structures. So, to jump into our first example, whenever you are first constructing your Lewis dot, we need to decide what the center element is, and then all the other elements usually are attached to it. Sometimes the formula will identify this element that's in the center because it's the element that you only have one of. For example, if it were CH4, well, we only have 1 carbon, it's very likely that will be our center. But here we have 1 carbon and 1 chlorine. So then we look to one other guideline. We'll choose the element that has the lower number of valence electrons. That will be our center element. That will lend itself to the greatest variety of bonding most times. So, carbon will be in our center, and we have 1, 2, 3, 4 valence electrons it brings. It doesn't matter. I will respect the 4 sides because we have a total of 4 elements that we're joining, but you have the choice as to where you would like to place your hydrogens and then your chlorine. You really have the freedom to do that. Chlorine being a halogen, it brings in 7. Now, hydrogen is an exception to the octet rule. Because hydrogen is only in need of gaining 1 more electron to fill its 1s, the first energy level only contains the 1s sublevel, its stability is an exception to the octet. It is fine with 2. So, carbon needs an additional 4. Well, if hydrogen would share its electrons with carbon, but then carbon vice versa, then all of my hydrogens momentarily would have 2, 2, and 2. Carbon now has 2, 4, 6, 7, so we need to pick up 1 more. Well, if we share 1 with chlorine, that will satisfy carbon, but I need to move that electron to show that now it will be assumed to pair up. So I'm going to draw this a little more vertically so that I can definitely tell that The sharing is happening between the element symbols. So I have carbon with 4 single bonds, no lone pairs. Chlorine with 3 lone pairs. That would be the structure. Hydrogen is an exception, does not need 8. Everybody is good. It would be absolutely fine if you would have put your chlorine on the right, but it will have 3 pairs, and then your hydrogen, 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 as long as the single bonds are there and no lone pairs. Okay, moving onward. This is actually ammonia. Nitrogen would be our center. It is the only single electron and plus. Hydrogen can only form single bonds. So it's very limited in its variety, but yet it's nice to know we're always going to form single bonds with hydrogen. Nitrogen comes in with 5. 1, 2, 3, 4, 5. So I'm going to place my hydrogens right where that single electron is with nitrogen. Then nitrogen has 2, 4, 6, 8, and each hydrogen has 2. We're good. All right. Okay. Now with carbon. If you have more than 2 carbons in your structure, it is incredibly likely that the carbons will be bonded to each other. So I'm going to go ahead and place those next to each other. Now, I just said that we're making small structures with an element in our center, and then we'll build on that center and not have chained molecules. But here we do. We will definitely attach our carbons to each other. That is what we're going to see when we have more than 1 carbon. And then the rest will be distributed equally unless otherwise told that. So since I have 2 hydrogen, I will place 1 on one of the carbons and 1 on another. We know hydrogen is going to single bond, and we know these carbons are going to bond. So carbon comes in with 4, but when it single bonds with the hydrogen, it now has 5, and then making that single bond, it now would have 6. 2, 4, 6, if momentarily they all would be on carbon. And the same with this one. So this carbon needs 2 more, and this carbon needs 2 more. So why don't we bring up these electrons? That will form a double bond. 2, 4, 6, 7. So we're actually going to bring down this additional pair to make a triple bond. I should make those a little closer to each other so they're not extending beyond the element symbols. There we go. And we're satisfied. It's absolutely fine if you would have made this triple bond and maybe put the hydrogen up here, and that is absolutely fine for the Lewis dot structure. Absolutely fine. All right. Now on to N2. Nitrogen comes in with 5. So each needs 3 more. Oh, I should have drawn that a little bit better. All right. Now, I know that some teachers you may have had before draw the electrons and each element a little differently. And that is fine. They may draw open circles or X's. That is okay, although Lewis dot structures, traditionally they are dots. So that's how I will draw them. That's how you see that Zumdahl draws them. So that is the way that I always approach it. Okay, each nitrogen needs 3 more. That gives each another. If we double bond, well, here we need to triple bond, so let's move those electrons over. And if you would have had, let's say, a pair here and a pair there, it's totally fine, as long as you have your 3 pairs between the element symbol and then your 2 lone. Just really quickly, going through this one. Okay, so is carbon or oxygen our center? Well, carbon will be our center because there's only 1 of it, and we just have 4 valence electrons versus 1 of oxygen, but it has 6. Okay, and it doesn't matter where we want to put our hydrogens. How about here and here, and put our oxygen here? We know that our hydrogens will just need to share 1. Then carbon has 2, 4, 6. It needs 2 more. Oxygen needs 2 more. Let's double bond. again, I just need, and it doesn't matter if I move that lone one there or that lone one there. So carbon octet, 2 each on hydrogen, and oxygen is good with its 8. All right, now SO2 teaches us something that we haven't seen so far. So oxygen will bond to sulfur. Everything comes in with 6 valence electrons. All right, now here's definitely a tip that I have, that when we have more than one oxygen in our structure, please bond one oxygen at a time. Sometimes we start to make single bonds, and that can just make it a little chaotic and definitely cause us to have to start again. So I'm going to satisfy this one on the right. It needs 2 more. Sulfur needs 2 more. So let's try to double bond and just see where that leads us. Let's go ahead and bond those and bond those. All right, satisfied, and actually now our sulfur, 2, 4, 6, 8, it is satisfied. Oh my goodness, so what do? This oxygen is in need of 2 more electrons. Sulfur, we're going to try to not exceed its octet. Well, what if we would let oxygen keep the 6 it brought? 2, 4, 6. Could sulfur donate its electrons to form a bond? Sulfur, even though it is sharing its electrons, it is winning. Bonding lowers everyone's energy. So I have bonded sulfur to oxygen and oxygen to sulfur just from the electrons of sulfur. Sulfur lowers its energy, and so does oxygen. And this octet is not exceeded, but the octet is satisfied for oxygen. That is called a coordinate covalent bond. And that is where all the electrons for sharing come from one of the elements. All the other bonds, each element sharing donated 1 toward the sharing. If they're coming solely from one element, it's called an coordinate covalent bond. Although electrons are electrons. So I mean, this bond won't behave any differently than any other single bond. But that just is acknowledging how we were able to make that action. It's very unlikely you'd ever be asked to identify a coordinate covalent bond within a compound, but we just have to understand that we can rely on that to accomplish bonding. So that is an introduction. The next thing I'd like to show you are constructing polyatomic ions.